Okay, so we're going to talk about the inverse of a function, and this should be review of grade 11. So if I start with a function and I call it f at x, I know that it takes some x's and sends them, so x's are my input, and it goes to some y's or the outputs. So the ordered pair would be xy. F inverse, because remember the notation, an exponent, it looks like an exponent, -1, but it's not really an exponent. It's notation for inverse of x, goes backwards. It starts with y and goes back to the x. So the ordered pair would be yx. So inverse literally means to switch x and y. So we're going to talk about graphing and finding the equation. So let's take a look at something we know, f at x equal to x squared. I'm just going to get a quick sketch of what that would look like. It's the basic parabola. The vertex is 0, 0, and it's a normal pattern opening up. So it's 1, 2, 3, 1, 4, 9. So I'm going to put my vertex at 0, 0 and go over 1, up 1 in both directions. And that's going to be enough to get the shape that I want. So this is f at x equal to x squared. To get the graph of the inverse, what I'm going to do is I'm going to take any of the ordered pairs and swap them around. So 0, 0 actually stays 0, 0. -1, 1 will become 1, -1. 1, 1 will stay 1, 1. And if I join them up, I get this, which is f inverse of x. So I use the inverse notation. I am going to get the equation in a minute. When it comes to symmetry, if we looked at the line where y and x are the same, any points on that line stay the same because 0, 0, if I flip it around to 0, 0, it doesn't change. Same with 1, 1. So the inverse will always be a reflection in the line y equal to x. If your x and y scales are the same, that will be the 45-degree angle line going through. You just have to be careful if your x's and y's, or the scale on your x and y are different, because then it's not quite a 45-degree angle line. And if we can connect this back to the definitions we've been talking about lately, f at x is a continuous function, but it's not one-to-one because it would fail the HLT. So because my original function is not one-to-one, when I invert it, it would fail the VLT, so it would be not a function. So for the inverse of a function to be a function, the original has to be one-to-one. Let's look at how to find the equation though. If I start with f at x equal x squared, I'm actually going to switch it to work with x and y notation because it's a little bit easier. So I've done nothing there but replace the f at x with y. Now I'm going to start the process of finding the inverse. So step 1 is to switch x and y, and then step 2 is to solve for y. So to isolate this y or get rid of the exponent 2, I need to square root it. And because I'm not making any assumptions, I say there's a positive and negative square root, because the positive square roots represent the top part of this, and the negative square roots represent the bottom. So therefore, f inverse of x would be positive plus or minus the root of x. So to graph, we switched points. To find the equation, we switched x and y and then isolated y. And I can also talk about domain and range. If I go back up to my original, it's a parabola. So the domain is all real numbers because this original parabola will eventually open all the way left and right. And the range is y bigger than or equal to 0 because the lowest point is 0 and it opens up. I could get domain and range of the inverse by looking at it, or because we are switching x and y, I can switch my domain and range. So because my domain was xer, my new range is going to be yer. Because my range was y greater than or equal to 0, that's going to switch and make my domain x greater than or equal to 0. And if we compare that to the green graph of the inverse, eventually it will open all the way up and all the way down, which matches xer, and it starts at 0 and goes to the right only, which matches yer for the range, x greater than or equal to 0 for the domain. I'm going to do one more, working with a line. So y equals -1/2 x plus 2. So if I were to ask to graph this, A sketch is fine, but my y-intercept is positive 2, and my slope is down 1 over 2, or up 1 back 2. This is 1-to-1. It is a function. Now I'm going to get the inverse. So 0, 2 will become 2, 0. And 2, 1 will become 1, 2. And if I was on graph paper, it would look a little bit more perfect. But I do have symmetry about that 45-degree angle line. And now if I want to find the equation for my inverse, I'm going to switch x and y. And now I'm going to solve for y. So I'm going to bring the 2 over and subtract it. You can think of this as a fraction, or I can think about this as a divide 2. So the inverse or opposite solving a divide 2 is times 2. So I'll end up with 2x minus 4 equals negative 1y. Now I'm going to divide by negative 1 on this side, and I'm going to end up with a positive 4 and a negative 2x. You could have wrote it as negative 2x plus 4. I just am used to moving my positives to the front to hold those negatives, and that would be my equation of the inverse. For this one, my domain of the line is xer, and my range is yer, so it'll be the same for the inverse. My domain will be xer, and my range will be yer. And I just want to do one more. That's not a line or parabola because we've been working with those since grade 11. So I'm going to look at g at x equal to 1 over x plus 2. I'm going to find the equation of the inverse, and I'm going to show that the inverse is a function, and I'm going to figure out the domain and range of the inverse. I'll let you see the function. So g at x equals 1 over x plus 2. So to find the equation of the inverse, I'm going to rewrite using y notation. This isn't a necessary step. You can go right to where you switch x and y. But I want you to see what I'm doing, that I'm considering g at x as y, because function notation just replaces the y values. And now I'm going to solve for y. I don't like solving when this is on the bottom, so I thought about this x as being x over 1, and I'm going to cross multiply. So I'm going to get xy plus 2x equals 1. So I went x times y, x times 2, and 1 times 1. And now this is my y term right there, so I'm going to work to isolate that. So I get xy equals 1 minus 2x. So then y equals 1 minus 2x over x. So then using function notation, that means g inverse, because it's related to this function named g, it's the inverse of it, is equal to 1 minus 2x over x. Now, to show that it's a function, I really want to show that the original is 1-to-1, because if the original is 1-to-1, then it is a function. And I'm going to work at C, which is asking about domain and range at the same time. Because if I look at this original, we haven't really graphed a lot of functions that look like this, but hopefully you can see for this that my domain is everything except negative 2. Because if I put a negative 2 in here, I'm going to get negative 2 plus 2, which would give me 0. So I'm going to try and get a sketch of what this looks like. When we have restrictions, we get asymptotes. So I know there's going to be an asymptote at negative 2 because negative 2 would make the bottom equal to 0. Now I'm going to pick some values on either side to see what's happening with this. You could use graphing software if you wanted to. I'm going to put 0 in here. So 0 would be 1 over 0 plus 2. So if I put in 0, I'm going to 1 over 0 plus 2. I'm looking at g. And so that's going to be 1/2 or 0.5. So 0 is going to be at 0.5. I'm going to figure out what's happening at negative 1. So if I put negative 1 in there, it's going to be 1 over negative 1 plus 2, which is 1 over 1, which is 1. Okay. Now I'm going to put negative 1.9 in because I want to figure out what's happening as I approach this asymptote. So I'm going to have 1 over negative 1.9 plus 2, which is 1 over 0.1, which is going to give me 10. So I'm going to be swooping up. And now here, the bigger number I get, the smaller fraction. I'm going to have 1 over 3 plus 2, 1 over 4 plus 2, 1 over 100 plus 2. But they're all going to be positive, so it's going to swoop like that. I'm going to pick some numbers over here on the other side. Negative 3. I'll have 1 over negative 3 plus 2, which is 1 over negative 1, which is negative 1. So at negative 3, my graph's going to be at negative 1. And if you continue to fill in and pick some values or go to graphing software, you're going to get something that looks like this. This is a one-to-one function because even though these are leveling out, they never become truly horizontal. They keep getting smaller and smaller and smaller. So I cannot draw a horizontal line anywhere that will connect with this function twice. So because g of x is one-to-one, g inverse of x will also be a function. I already did my domain by looking at what are the holes, and now I'm talking about g right now. Sorry, I should have made that clear. So for the original, I can't have negative 2. And if I look at my resulting sketch, there's no way y can be 0. It's above 0 and it's below 0, but I can't take 1 over anything and make it into 0. So my range is anything except 0. So now for my inverse, and they never really asked me to graph the inverse, but I could by flopping this around. I'd have a horizontal asymptote at negative 2, and I'd pick these points and flop them around. But I never asked you to do the graph. I just asked for the domain and range. Well, because I have the domain and range of the original, I can flop them around, and I will have the domain and range of the inverse. So x not equal to 0 translated into y not equal, x not equal to negative 2 translated into y not equal to negative 2. And y not equal to 0 became x not equal to 0. My domain on the original is the range on my inverse, and the range on my original is my domain on my inverse. So I want you to, in your textbooks, take a look starting on page 27 and take a look at questions 1 to 10. Most of this should be review from last year.